Hello class 9 students. Today I will cover the exercise number 1.4 and 1.5 in your NCERT book of class 9. So we will first look at the representation of real numbers on a number line. So the number line should be clear to you. So what we do is that we have integers marked on this number line. This number line extends from minus infinity to plus infinity. In the middle we generally have 0. We have negative numbers on the left hand side of 0 and positive numbers on the right hand side of 0. Now suppose I want to locate 2.665. So I understand that this is a number greater than 2 and less than 3. So it will be located between 2 and 3. So you need subsequent magnification because ultimately on one number line you will not be able to go to so much of precision. So what we do is we take a part of it, we magnify it, and then we subsequently keep magnifying till whatever decimal place we want the representation to be. So here I want 3 decimal representation. So I will look at the numbers first. Between 2 and 3 this will lie. And inside this, you know that it is basically greater than 6. So 2.6 and 2.7 will be the outliers for this particular 2.665. So here first we magnify the 2 to 3 region. And then 2.5 here is marked in the middle. I know that I have to look at this 2.6 and 2.7. I have to magnify this. So on subsequent magnification, I divide it further into 10 parts. So I have now 2.61, 2.62, 2.63 and so on till 2.69 represented between 2.6 and 2.7. Now we are looking at 2.66. So we will magnify 2.6 to 2.7 region further on over here. So here I will look at further magnification. So this magnification is done. Now I will again divide it into 10 parts. So I will have 2.661 to 2.669 represented here. And what was the value I was looking for? 2.665. So this is the value that we were looking at. So by successive magnification, I can represent the values. Now in example 11, suppose I want to represent 5.37 part. It means 5.3777 is the value that I have where 7 is recurring. And it is being told to me that I want 5 decimal precision. So till 5 decimals I will write this value. So it's 5.3 and 4 sevens here. Now what will I do? I know that this number is between 5 and 6. So I will first magnify that. So here then I know it's 5.37. So I will magnify the 5.3 to 5.4. So 5.3 to 5.4 is magnified here. On subsequent magnification, there are 7s repeated. Then I will take the 7 values, so between 7 and 8 I will magnify and I will keep doing it till whatever precision I want. So I wanted 5 values, so I will magnify it those many times and I'll be able to get the value here. So in this exercise 3.765, you will actually start with, let me just show you one example. So 3.765 is what we want to represent on the number line. So I will start with the number line. So I know this value will lie between 3 and 4. So I will magnify this part. On magnification, I will divide it into 10 equal parts. And this is 3. So this will be 3.1, this will be 3.2 and so on till 3.9 and 4. So I wanted 3.76. So I will locate the 7 part. So obviously this will lie between 3.7 and 3.8. So I will further magnify this part. On magnification, on further division, I will look at this will be 5, this will be 6, this will be 7. I will look at the 6th value because this is greater than 6 but less than 7. So then I will magnify this part. And further on, I will look at the middle value for this. So this would be 3.765. So you can go as to as many decimal places as specified in the question. Now suppose I have 4.26 where 26 is repeated and it's been told 4 decimal places. So I will write like this. So I will magnify something between 4 and 5. Then on the next one I will magnify between 2 and 3. On the next iteration I will magnify between 6 and 7. Then in the next iteration I will magnify between 2 and 3. And in the last, I will point out to the 6th value. So this is how you do in the subsequent magnification and get the value. Now moving on to the next chapter. Now operational real numbers. So you already know there are certain properties. There's commutative property, associative property, distributive laws of addition, and multiplication. So I will briefly go through them one by one. So you have closure property. Closure property is when you basically, suppose I'm talking about real numbers. So if I add two real numbers and I still get a real number, then real numbers are supposed to be closed with respect to addition. So two real numbers are subtracted and I still get a real number, then the real numbers are supposed to be closed with respect to subtraction. Similarly, for multiplication and division, if I perform multiplication on two real numbers and the product is still a real number, then it is closed with respect to multiplication, and similarly for division. If you remember, commutative is simply in terms of addition, if I am saying. So this is the operation that I am doing. This is commutative. Associative is when I am able to add in different ways. So this is associative. Distributive would be when I have something like this. So this is xy plus xz. So you can just refresh your previous class books in case you do not remember them. Now here you're trying to analyze whether all these properties hold for irrational numbers or not. So they have taken a couple of examples here. Now let's look at them one by one. So what will happen if I add an irrational number with a rational number? So if I do something like 2 plus root 3, you already know that this is non-terminating. So adding any other number will not make it terminating. So this will still remain irrational. Similarly, multiplying a rational number with an irrational number, it will still be irrational because multiplying with any rational number will not make it terminating. So it will still be an irrational number. So to check whether 7 root 5, 7 divided by root 5, root 2 plus 21, pi minus 2 are irrational or not. So if you look at this, if you multiply root 5 with 7, so here you're multiplying a non-terminating decimal number with a constant, it will not make it terminating. So this will still be a irrational number. Similarly, 7 upon root 5. So 7 upon root 5 can be written as, I can just multiply root 5 and root 5 here. This still remains the same. So this becomes 7 root 5 upon 5. This is actually equal to 7 by 5 into root 5, which still remains an irrational number. Similarly, addition will not make it terminating. Subtracting will not make it terminating. So these still remain irrational numbers. Now there are certain examples given here. So you want to add them up or add these. So adding 2 root 2 plus 5 root 3 and this. So it's basically you can combine them like normally you do using all the properties here. So I'll combine root 2 here, root 2 here. So this becomes 3 root 2 and 5 root 3 minus 3 root 3 would be 2 root 3. So this is the answer that I get. Square root of 5 multiplied with square root of 5 will give me 5. So this will be 6 into 5 into 2. So 60 is the answer. Divide this by this. You can write root 15 as root of 5 into root of 3. And then you can cancel this out. So this is normally like you do all multiplications and divisions. All those rules apply here. And you'll be able to solve them easily. So the facts are that sum or difference of rational number and an irrational number is irrational. The product of quotient of a non-zero irrational number with an irrational number is still irrational. If we add, subtract, multiply or divide two irrational numbers, the result may be rational or irrational. So if I have something like 8 root 3 divided by root 3, then I'm dividing two irrational numbers, but my answer is 8, which is a rational number. Similarly, in subtraction, I could have been cancelling it out. So I have 6 root 3 minus 6 root 3, then the answer is 0, which is actually a rational number. Even in addition or multiplication, the answers may be rational or irrational depending on the values that we take. So here what is discussed is that we were making on the number line root 5, root 2, all those values we had seen earlier, how to represent them on the number line. Now here you are given an example as to how to represent any number. So it could be a square root of 3.5 and you're trying to represent it using this method here. So I'll just demonstrate it. So here we first draw a line of the line segment that we want. So I mark 3.5 here because I want root of 3.5 to be represented. Then I further on add 1 to it. So I mark a 4.5 here. Find the midpoint of this segment 4.5 now. So this is the normal method which you've used before to find the midpoint. Once the midpoint is got, I take this as the center and draw a semicircle as shown here in the diagram. I mark a 90 degrees at this point that we had drawn earlier. You could use a protractor to do this. Now this length should be root of x. Now to be able to understand the proof of what we've done is, so the process is that suppose I want to represent root x here, what will I do? I will first draw a line of length x here, add another one here. So this is 1. Take the midpoint of this. So how do I take the midpoint? You take an arc here typically like you do. Join them and you'll get the midpoint here by joining them. And I draw a semicircle here. Forgive my drawing here because I'm not used to this. At this point I constructed a 90 degrees line. So this was 90 degrees. This should give me root x. Now let's look at the proof of this. So suppose this is O, this is A, this is B. So I'm looking at this right angle triangle OAB. I'll draw it separately, the OAB here. This is OAB. Now if you look at the sides here, so the radius of this circle would be x plus 1 divided by 2, because I have taken this entire length and found out the midpoint of this. So this is the x plus 1 divided by 2. So OB is actually the radius, because you can see here this is joining this. So it's a complete arc from here if I join this. So OB is actually x plus 1 divided by 2. Now let's look at this value here. So this was, now let's carefully look here. So what is OA? OA should be, because this is x, so OA should be x minus this radius here. So OA should be equal to x minus x plus 1 divided by 2, because that's my radius. So this is actually equal to, if I take 2x upon 2, so 2x minus x minus 1 upon 2, which is equal to x minus 1 upon 2. Now using Pythagoras theorem, you know that OB square is equal to OA square plus AB square. So AB square should be equal to OB square minus OA square. This would be equal to x plus 1 divided by 2 whole square minus x minus 1 divided by 2 whole square. So you already know the formula A square minus B square is A plus B. So A is this into A minus B. So this is equal to x into 1, that is x. AB becomes equal to root of x. So that is why this value is actually equal to root. So by this method you should be able to depict any root value on your number line. So once this is got, you just simply need to project the same length on the number line to be able to show it. So here they've taken the projection. What will you do? You will take this as the center, so this will become your O, and with this radius you will just drop it on the number line, and this part will now start representing VE will be your root x. So then you have nth power of any number. So this is basically saying x to the power 1 by n. So this is your exponential or your indices which you studied in your previous classes. So there are certain formula that you need to remember. Root of AB is actually equal to root of A into root of B. Similarly, root of A divided by B, you can take the individual square roots and divide them. This into this, so A plus B into A minus B used to be A square minus B square. Similarly, when you take root and square it up, it will give you A minus B. So here you don't really need to learn these formula, but I mean you should be able to do them yourself using the standard formula. So if you have, so a basic formula of x plus y into x minus y should come in handy. It's like x square minus y square. So here if you take a square minus root of b square, this will actually give you a square minus. So these are the formula which they've told you here. So they're very simple. Here also the same principle. And you'll be able to get the normal x plus y into x minus y kind of formula, x plus y whole square formula. This will all work here. Now moving on to the exercise here. So you just need to open it up. 5 into 2, 10 plus 5 root 5 plus 2 root 7 plus root of 35. Because root of 7 into root of 5 would be root of 35. Here, so 5 into 5 minus root of 5 square. So 25 minus 5, 20. So you could simply solve these using the normal formula that you remember. Now rationalizing the denominator. So here there's something called a conjugate. So if I have been given something like this, how do I rationalize it? Rationalization means I don't want any irrational number in the denominator. So I will simply multiply the numerator and denominator by the same number, so I'll get root 3 upon 3. Now this is the rationalized. 1 upon root 2 is root 2 upon 2. Now when you have addition or subtraction in the denominator, you could just multiply with the conjugate. So let's take an example. Suppose I have 1 upon 4 minus root 5. Now the conjugate of this would be 4 plus root 5, the opposite sign, and I'll multiply it both to the numerator and denominator. So my numerator remains this and my denominator becomes 16 minus 5. So this is actually equal to 4 plus root 5 upon 11. Similarly, for an addition, you will multiply with the negative conjugate. So in this manner, you should be able to rationalize these numbers, the denominators. These are some examples. Now moving on to the exercise. So classify this as rational or irrational. So this is obviously irrational because you're subtracting root 5 from a rational number. It will still remain irrational. Here if you open up, root 23 will cancel out. So this will become a rational number. Here root 7 cancels out. So this becomes rational. This is an irrational number. This is again an irrational number because multiplying with an irrational number still makes it the same. Simplification you could do like you did before. Recall pi is the ratio of circumference of the circle to its diameter. So this was how pi was derived. This seems to be a contradiction to the fact that this. How will you resolve this contradiction? Actually, there is no contradiction here. Whenever you're measuring with scale, there is some approximation because the least count of the measurement tool is always coming into picture. So you really can't get an accurate measurement. So that is why there is no contradiction here. Now represent this on a number line. So you could simply use the method that I told you. Draw x, then another, take one more, and then draw an arc using the midpoint. So you should be able to do that. Rationalize. So you will multiply this by root 7 upon root 7. You will multiply this by root 7 plus root 6 on both the numerator and denominator. Here the conjugate would be root 5 minus root. Here the conjugate would be root 7 plus 2. So this solves your exercise here. So I will see you in the next class. Thank you.